Yeah, I priced out like an insanely powerful build with like huge amounts of RAM and great graphics card and all sorts of stuff, and I was like, ugh, $3,000. Yeah, I was like, let me lower my standard a little bit. I got it to a more reasonable 1,500.
That's how much mine was when I got mine, but that was because of
Lance
graphics
Trainer.
cards being scaled.
Mm-hmm.
That was just like if
Oh.
it's on the GPU.
Memphis Burroughs,
That thing was $2,000.
Morgan
A few years ago.
Riley.
What's in it?
Morgan
I don't
Riley,
remember.
Oh, you bought it a while ago.
Jaden Gibbs. All
Thank
right, sure. So first thing, any questions about anything we've covered up to this point at all? Anything at all? I want to mention a few things about this. If you have the probability function for x and you want the probability function for y, probability density function. And the reason I'm saying this is, in general, if you have a monotonically increasing function, you don't have to worry about this. And I'm going to just first make the general statement that what they actually say is you have f of y, that's why this is the probability density function for y, dy, that's equal to f of x dx. That's true, but there are specific cases where you have to change it, and that's when there's even functions. When you have functions, or I should say functions that are like squares, fourth power, any kind of function like that, where you have y is x squared, and I'm going to try to say this in a way that's clear. So really what they'll say is that if you have f of x and you want f of y, you're going to have f of x, and then you're going to replace x by y. So what you're going to do at this point is put in whatever the function of y is, the inverse. If you have like y is equal to g of x, then you could say x is g to the minus 1 of y, however you want to write that. But what you're implying is everything will be a function of y on the other side of this. Follow me, class? Because the argument is y. So this would be, I'll put this down as g to the minus 1 of x. And really, it is going to be a function of y, so it is a function here of y. Then you're going to have dx dy. And this is the kicker right there that you have to be careful about. So if you look, and the classic is y equals x squared. If you take a look at this is the random variable y is equal to the random variable x squared. This is the classic one. Whenever there's small letters, it means an exact value of y or x. When they're large letters or capital letters, it implies that they are random variables. It's the only difference. So if you have this and you plot it, last time I didn't say this the way I wanted to. Y and x, you're going to get this. And I think everybody understands this. This is going to be x squared here. Now, when you think about the density, probability density function, if you think about this for a second, if we have a value of x, and the width of this is going to be dx, so I'm going to try to do this as best I can. Here, we're going to have dx, but it's at a value centered at x. You have a value of y here, and this is dy thickness, and the probability that it's between these 2 points here and here. Can y'all follow me on this? Y, it would be centered at y with a spread of dy. It's going to be dy times f of y, But you'll notice also, not just this value of x can cause it. Down here, if you go to the conjugate point, we call it conjugate, this has a width of dx here, or small dx, I'll put it that way. And you look up here, that also will give you the same value of y. So when you talk about the probability density function for y, there are 2 possible values of x that would imply that. So in other words, if you take a look at this, f of y dy implies the width here in y. Think about that. You remember how the density function in general, if you have f of x and you integrate dx from like a to b, that's the probability of x being between a and b. Is everybody with me on this? Well, in this case, when you have dx from here to here, yeah, that's the probability of y being from here to here, but also if it's negative x, it has that probability. You follow me? So these are even functions. Anytime you have like y equals x squared, y equals x to the fourth, functions like that, or y equals cosine x, that's an even function. You're always going to have to include both the positive and negative sense of x. And the way you always do it is, for this one, the smart way to do it is you take f of y, and I'll just put it f of y dy will be equal to f of x, and you might say of minus x times dx, right here, plus f of x, positive x, dx here. And in the book, he goes through this a bit. Did anybody read that section in the book on this? Anybody? You did? Now, he brings this about in a way where he discusses it, I think, a little more in depth mathematically, but the essence of what I'm showing you right here is the key. So the way he's going to do it in the book is, put it right here, he's going to say, if I want f of y, assuming I have f of x, f of y, that's going to be equal to, and then he's going to have f of x, and here it's going to be, we're going to replace this, but it would be the replacement for minus x plus f of x, replace this with positive x, and then just take the absolute value of the derivative of dx dy, and that should do it all the time. How many took a look at these problems? I'm just curious. If you took a look at them and did them, you'll notice one thing. When you're going through them, especially odd-even functions can trip you up. And I know that for a fact. Now there's a couple other tricks here too that I'll tell you about. So anyway, best way to do this is probably with a simple example. And which one is he given in the book? I just put this down, but I'm gonna do this. This is a problem, I think it's problem 2-3.3. You can write this down. I'm gonna do it over here. I got it. Because I don't usually teach this class, I don't have a whole lot of, you might say, classic examples from my research that I use. My research, a lot of stuff I'm doing is on radar. But downfield from this, we're going to get into stuff that I'm very familiar with, and I'll bring all those examples. But this part of the course, I just don't have at my fingertips a whole lot of examples or problems other than the book. And these are just to get you familiar with how to approach problems of this class. So, in this one, with probabilities, 2-3.3, I think they give f of x is equal to e to the minus 2 times the magnitude of x for all x. Can anybody confirm that? Well, here. You got that? You did this problem? Thank you. If you look at this, take a look. It's an even function. And what he's really doing is this. It looks like this. This is f of x versus x. It's doing this. It's an even. By the way, does everybody know what I'm talking about when I say even function? I'm going to say this for everybody's sake. Some people actually don't. When you have an even function, it means that f of x is equal to f of minus x. In plain English, it means if you find a point here for a positive value of x, and you go to the negative value of x, it's the same value for f of x. That's an even function. An odd function, if you had odd, it means f of x is equal to minus f of minus x. Give you a good example. Obviously, anything where you have y equals x squared, y equals x to the fourth, those are going to be even functions. With me, class? And the classic odd function is y equals x, or y equals x cubed, or y equals x to the fifth. Because any positive value have the same magnitude as any negative value of x, but it'll have the opposite sign. That's the only thing it means. Another classic example of even in terms of trig is cosine x, odd sine of x. These are things you have to understand. And while I'm at it, might as well say this. When you have an odd function times an even function, it is an odd function. With me on this? And if you have an odd function times an odd function, it's an even function. And if you have two even functions times each other, it's going to be an even function. Follow me on, everybody? Now that'll be important in evaluating certain things. It'll make it a lot easier and clearer. Anyway, for this one, this is the density function for x. We're after fy of y right here. That's our goal. We don't know what it is. And some of you are thinking in the back of your head, is this on the quiz? It might be, but I'll try to be clear later. Parts of this type of idea, at least, you need to understand fairly well. You're going to see how this rolls into some things in a bit. So, if we have that, we want that. First thing, we need a function that we're talking about. So we're going to say x squared is equal to y. And that's what I had up a second ago. Now, if you look at that, that's an even function. Agreed, class? If it's an even function, we go right to the form f of y is going to be equal to f of x of minus x plus f of x of positive x times the magnitude of the derivative of x with respect to y. Nothing tricky, I just repeated, I think, what I had over there. Follow me? Make sure you get this idea too. You're going to see there's a clever way to do this. We can just double either one of those because they're going to end up being the same value. All right, now coming down here, we have x is equal to, and I'll put it a square root symbol, square root of y, or to the 1/2, and that means dx dy right here will be equal to, and this is going to be, when you take a look at this, that's going to be plus or minus 1 over the square root of y. The way I like to do these, by the way, is I'll have x here is equal to y to the 1/2. So when I take dx dy, I forgot the 2 by the way, then you're going to end up getting 1/2 y to the minus 1/2, but there has to be a plus or minus on that. Agreed, class? Y'all understand what I'm doing here? I'm spending a little more time on this than I usually do. But so come over here, and now we do it. For this one, we're going to have f of y equal to f of x, or now it's going to be e to the minus 2. And it's still, on this one, magnitude of x. So when x is minus, it's just going to be square root of y. Well, I should put a small y there. Plus e to the minus 2 square root of y. And then you're going to have this value, which is going to be times 1/2, and it would be 1 over the square root of y. I think I put the solution for this one actually on OneNote. I'm not sure, but anybody recall that? Yeah. Okay. It makes it easier to see that solution. Okay, if I have this, and that's the probability of density of y, I can just double this right here. Can you all see this, class? These two are identical in every way because it's absolute value. So just double that, and in doing so, I get rid of that. So my density function looks like this over the square root of y. That's the first part. I'm going to tell you one thing. There's parts on this one. You don't want to use this for an integration. That takes more time. You can do it. You know, if I ask you, and you're gonna see where this fits in, because we're gonna get into average value or expected value. We're gonna mean squared value and the squared value, expected value of the squared operators. This integration, this times y, just y or y squared, it's a pain. Your calculators are your saviors, though. You can use them in this class, and they do integration. How many have calculators do symbolic integration? I think the standard ones they recommend do it, but I'm not sure. I know. Is that my fault? I thought the elections were. All right, anyway, your calculator should be able to handle integrations, especially with hard limits. Please make sure by Friday you know how to use your calculators to do that. And some of the problems that we're going to talk about, we'll use those. Now, that's the first part of this problem. The second part is the probability that y is less than 0. Is that
Y is greater than 2.
less than 0, greater than 2?
It just says greater than 2.
All right, forget it. All right. So greater than 2, we're going to do it over here, but I want to make, I got a point on this one. So for part B of this problem, they want the probability that y, and it's random variable y, or actually, it doesn't have to be because it's an exact value. Y is greater than 2. There's a couple ways to do that. The most obvious way, since the value of y for y equals x squared here, if we plot that, y can only be from 0 positive to infinity. With me? So the probability that y is less than 2 would be really the integral from 0 to 2 of the probability density function of y dy. Do y'all agree with that, class? All right. You could also say, I'm going to put two things up there. You could say it's 1 minus the integral from 2 to infinity of the density function f of y dy. In other words, you're doing now another form of integration. Sometimes that's easier. But both of these are a bit of a pain on your calculators and on your, I mean, I looked at this problem, I think that's stupid. At least that's my thoughts on this. If we want the probability that y is less than or equal to 2, go back to this drawing for a second. That's the probability that x right here is going to be square root of 2 positive, square root of 2 negative. Do you all follow me on this, class? I'm going to see this right here. In other words, if you think about this, the probability that y is 2 or less, in other words, below this value right here, that it's less than that, well, that would be f of y dy from integrated from 0 to 2, correct? But it is also essentially the integration of f of x from minus 2 to 2. It's the same, that you're basically doing the same problem. How many see this right here? Either one defines the same problem. Do y'all follow me? You got me on this? Okay. This is an easier integral, f of x integral. And matter of fact, we can even break it down further. I'm going to erase this part and try to really make my point, because this helps so much when you're doing problems that have a relationship between an f of x and f of y, a functional relationship. Yes, sir?
Why would you integrate from 0 to 2 if you're finding y is greater than 2?
No. Oh, is it greater than 2?
Yes.
Sorry. Then, I'm glad you yelled at me about this. This should be from greater than 2 would be 2 to infinity, right? And this would be 1 minus 0 to 2. My bad on this one. I'm very sorry about that. Y'all hear me on this, class? I apologize. Yell at me if I make a mistake. In not taking narcotics, I'm taking ibuprofen, but today the pain's down, but I'm still making mistakes. Anyway, you all with me, class? Back to this thing. What I just said, so the probability that it's y is greater than 2, now I gotta redo this one. So the probability that y is, we could do this one, maybe we will, and here's why. I think it'll be a little more in line. If I want the probability that y is between 0 and 2, I can take, if I have that, I can take 1 minus that to get the probability that y is greater than 2. Does everybody agree with that? All right, but I want this for a reason, because this one kind of showcases something. Here, if I'm taking a look at this, well, if I have f of, what I'm really going to integrate is f of x from minus the square root of 2 to 2. Do you agree with that? And the area under this curve would be the probability that is from 0 to 2. Now the important thing is, it's an even function. So I only have to integrate from 0 to square root of 2, because the area here, if you look at the area under this curve here, it's the same as the area from 0 to plus square, or 0 to square root of 2 is the same as the area from minus the square root of 2 to 0. Agreed, class? So now I'm going to say that this probability of the probability of y being less than or equal to 2 is the same thing as the probability of x being greater than the square root minus the square root of 2 and less than plus the square root of 2. And really, that's 2 times the probability of x being greater than 0, less than square root of 2. I want to do this one, then we'll get the answer to part A or part B of that, but I want to make sure you see this, because this, on your calculators, when you're doing these things, if you go the f of y route, you're going to run into kind of a complicated integration. I promise you really will. You can get irritated with it. So for this one, now I have 2 times the integration from 0 to square root of 2 of e, might as well get rid of the magnitude sign, minus 2x dx. And I think everybody sees that should be the integration, right? We're going to multiply by 2. And here, now I have 2 over minus 2, and I'm going to have e to the minus 2x evaluated from 0 to square root of 2. I'm going to tell you one thing about this that I do. First, everybody agreed that that would be the follow through in the integral? All right. Now, what I'm going to get rid of these 2's for starters. And I'm going to put a minus sign here. I usually say this one time. And you know how you deal with a minus sign like that? Just flip the limits and get rid of it. Follow me? Everybody see this? If I take the 0 and put it up here and the square root of 2 down here, get rid of the negative sign, it's the same thing. So now I have 0 here, square root of 2 here, and that is 1 minus e to the minus 2 times square root of 2. I'm going to leave it like that for a reason. And that's probability that x is between minus the square root of 2 and plus the square root of 2. Probability that y is between 0 and 2, correct? Everybody? Back to this thing. So the probability that y is greater than 2 is 1 minus that probability, and that value is going to be 1 minus e to the minus, and this is just going to be 2 square root of 2. And that is simply e to the minus 2 square root of 2. Y'all agree? I don't even know what the value of that is.
0.0591.
Okay. Everybody got that? Believe it or not, I'm trying to be not prophetic on this, but I'm trying to be clear. This kind of a problem even though in class I got it, looks simple, on quizzes and tests, it'll fumble people, because what they'll try to do is that integral with f of y. They're gonna try to do that, and that, people foul up integrations like that all the time. Now, your calculators, if you know how to use them, you can do it, but anytime you get like a square root, 1 over the square root of y, and you're doing integration, you gotta be real careful about some of the bounds on those things. I'm just warning you about, these are the errors, at least I can anticipate happening for some of the problems. This problem was, that I have here, I think it was useful to see that because it's the even function problem. Or it's a problem where you got possible negative values of x, but only positive values of y. And you have to account for it. Now, the problems where they just have a linear, a monotonically increasing function, I want to level with you about this. If I add, yes, sir.
So if we have the even function on those problems, can we like assume that we're gonna multiply f of x times 2? Like, will that always work, or do we need to go through the whole steps every time?
Well, I'm a little cautious to say it's always going to work, but if you have say you have a density function for x, right? And then you have y equals some function of x, and y is an even function. I can't think of, the problem is you can have an even function that does this, and this is the real problem. All right, if this is y and this is x, suppose my function is this. Follow me? Now you have negative values of y. Do you follow me on this one? All right, so you gotta be more careful on this one. If I want the probability, like the y is between, say, 0 and 5, and 5's out here. All right, well, if you gotta think about this now. The probability y is between 0 and 5. 0 is here. 5 is up here, follow me? Now, so there's going to be a corresponding -5 here, and this is the intercept. And now you're going to have a different, you might say, set of constraints. If you have y is 0 or greater, what you're really talking about, you got to find the intercept here of 0, right? And it would be x from here to here plus x from here to here. So it's going to have different constraining values, is what I'm trying to say. Y'all with me on this? You can, I mean, if you want the function for this, you could say y is equal to x squared minus 3. Now, when you talk about the probability, you have to actually look at the region you're talking about here and here, because it's not so easy. You can't just double it from here to here. Maybe you can double it from here to here. Well, with me, yeah, you could take the probability x is between here and here, and I'm being very loose about this. Yeah, that's going to be the same as x here to here because it's even, so you could double it from here to here. But you got to be careful that you just don't assume it starts at 0. Do you understand what I'm saying?
Yeah.
I don't try to make things too tricky, but you have to think it through a lot of times. I want to do one more. I'm going to try to do this quickly too. Too quick. So 2-3.4, and the reason I chose this is strict monotonically increasing, but there's, in my opinion, a trick on an easier way to do it, and I don't know if you actually, well, in the solution, I don't know if it was brought out, because the solution just brute forces it, whatever it is. So for this one, it says that y is 3x minus 4. And then they give you, it's the same density function, right? Let me try this one. You look at that? So they have f of x is equal to e to the minus 2 magnitude of x and it's true always, and you look at this functional form, if I have y versus x here, well, you know, 3 is going to be the slope of the line, right? It's basically, take a derivative of that with respect to x, you get a slope of 3. The intercept, if you look at this, when x is 0, y is minus 4. And it's a straight line, it's got a slope of 3. Something like this. So this is what you're talking about here, correct, class? So when he starts asking about things, and I'll do the inverse here. So I have x here is going to be equal to y plus 4 divided by 3. And then it's monotonically increasing, so I can easily say that f of y is going to be f of x, and then you're going to put in the value, the functional form, what x is in terms of y here in a second. And then you'll take dx dy. So here, it's going to be e to the minus 2, and it's going to be magnitude of y plus 4 over 3. And then the magnitude of dx dy is simply 1/3. And that would be fy of y. First, does everybody agree with that? Now, here's something I'm going to warn you about. You see that y, magnitude of y plus 4 over 3. I'd take the 3 out in front right away. Get it out from under the division, under this would be. Times that. Then the second, y'all follow me why I did that? I'm trying to just make this. So you see this, when you're talking about absolute value of y plus 4, if y is at a value less than negative 4, right, we can just get rid of this negative sign. But if it's at minus 4 up, then you have to leave the minus sign there. Y'all, everybody with me on this class? Because there's regions where this absolute value has to be into account. You always start where where's y plus 4 equal to 0? It's y equals minus 4. Anything less than that, you're going to do a different thing with the magnitude. And anything above that, you'll change it to. Can you understand the reason for what I'm saying? Mm-hmm. Okay, now for this one, he says, I think they want the probability of y less than 0. Is that right for that problem?
I believe so, yeah.
Y less than 0. So if I want the probability of y less than 0, right? This is the point I want, right? So the probability of y less than 0 is the same thing as the probability of x. You can think of it this way. X less than whatever this number is. What would that number be to y? When this is 0, what do you get? I mean, yeah, that would be 0 is equal to 3x minus 4. So x would be equal to 4/3. Do you agree with that, class? So this point would be 4/3 in x. And the probability of y right here is less than 0 is the same thing as the probability x is less than 4/3. Do you agree, class? Now that's not a bad integral if you stick with f of x. This is the way I'm going to do it. Can you understand? I'm trying to just use this density function and avoid the one I just developed to minimize the problems with integration. Now think about this. So if I want the probability that y is less than 0, that's the same thing as the probability that x is less than 4/3. And that would be, follow me on this one, that would be the integral from minus infinity to 0 of e to the minus 2x. Now that's a magnitude. Since I'm going from minus infinity to 0, I can make that a plus 2x dx plus the integral from 0 to 4/3. And here I just put in e to the minus 2x dx. You agree with that? I have to break it up into two parts because of that absolute value sign. There's an absolute value. It's minus e to the minus 2 absolute value of x. Everybody agree with that?
Why'd you take out the -2 on the first one again? Or
These are negative values, right? Remember, it was e to the minus 2 magnitude of x, right? When x is negative, right? I mean, you want to make sure this exponent is negative. Well, if all here x is negative, so I would have e to the minus 2 times the magnitude. Follow me? It's going to be the same thing as putting a magnitude there, because in fact, if you're integrating e to the minus 2x or e to the minus x from minus infinity to 0, it's the same thing as integrating what? E to the minus x from 0 to infinity. Do you agree with that? It's going to have the same signage in the integration, or the exponent. How many see this right here? Just think about it for a second. Here's what I'm really saying. If you have e to the minus, say, f of x is e to the minus 2 magnitude of x, right? So what's f of minus 2? That's e to the minus 2, right? Magnitude of minus 2, right? That's really going to be e to the minus 2, or e to the minus 4, pardon. Agreed? All right, go back here. If I take a look at that, if I make that a positive right there and put minus 2, it's the same thing. Now x is minus 2, so it would be minus 2 times 2 is going to e to the minus 4. Anyway, it's going to be less than 1, is my point. You see it?
Yeah. Why don't you take the magnitude out the second time? Because I guess the way that I'm thinking about it is if you took the
Well-
magnitude of minus, like if you plugged in -2 the second time.
Yeah, whoa, it's the x, remember, it's e to the minus 2 magnitude of x, right? Between 0 and 4/3, x is positive. I don't need, I mean, I took the magnitude out, I can leave it there, but I'm trying to make this an obvious integration. If I have e to the minus absolute value of x and I integrate it, I have two possible things the general form of the integration would have for the negative values of x and positive. Here, I know it's strict positive. So e to the minus 2 magnitude of x is e to the minus 2x from 0 onward, upward. Do you follow me?
Yeah, that one makes sense.
All right. You look at this and think about it, it should come to you. This is not mysterious right here, I promise you. Anyway, now this is the real point, the reason I did this. You notice I did not do the f of y integration here. I avoided it and I went to the f of x because it's an easier integral. That's the reason if you want the truth. Now, what is this value? Well, this is x, this is e to the minus 2 magnitude of x, right? It does this. You notice that's an even function? And you notice if it's a legitimate f of x, the integration of this function, this is f of x, integrated from minus infinity has to be 1. Do you agree? Just make sure you see this right here. So the area from 0, or from minus infinity to 0, has to be the same area as from 0 to infinity. How many see this? This helps a lot if you see this stuff. If that's the case, this value is
1/2.
1/2. Agreed? You see? Remember, integrating over that has to be 1. Since it is symmetric, and it's an even function, the area here has to be 1/2, this has to be 1/2. You're going to use this a lot with Gaussian integrations and very soon. It's coming up. So this is going to be 1/2, and then it's going to be plus. Now the integration of this is straightforward. E to the minus 2x dx is going to be 1. Well, technically it's 1 over minus 2. When you do integrate e to the ax dx, you get 1 over a e to the ax in a value. Then you get e to the minus 2x, and you evaluate it from 0 to 4/3, and here's the beauty. Now I have 1/2, and I just switch the limits here, then I have plus 1/2, and then I have e to the 0, which is 1 minus e to the minus 2 times 4/3 is 8/3. You agree with that? And what's that going to be? Well, that's 1 minus e to the minus 8/3 divided by 2. That's a small number. I don't know what it is, but. Did I even get it? So, wait a second. Did he add? What is that value? I shouldn't say, the e to the minus 8/3 over 2 is a small number. This is almost 1, right?
It's almost one, yeah.
0.91.
9653.
All right. If you look at the way it was done in solutions, I think they did the f of y dy integration. They broke it down to two ranges, didn't they? That's a
Yeah.
pain. I'm trying to tell you the simple way. And I warn you, this kind of stuff saves you on quizzes, saves you on tests. Just take a moment, step back and think about, well, which integration would be easier? Always look at that. That's my suggestion to you. What's the third part of this one?
Find the probability that y is greater than x.
All right, now how do you do that? That's a good one. I mean, I get it, but this is a question, and sometimes unless you see it asked before you see it on a quiz, you get in trouble. So the probability of y, they want the probability y greater than x, right? Well, here's y, correct? So the probability of y greater than x here would be 3x minus 4 greater than x. Do you agree with what I'm doing here? It's an inequality, correct, class? Just think about it. Now, I know I'm saying this now because if it's asked on a quiz, this type of stuff, because you didn't see it before, you get a little tense, your brain kind of locks up, and you kind of fumble it. So I want to make sure everybody sees this. If that was asked, or y less than x, or something like that. You can ask all these, just turn it into a mathematical statement. If you look at this, add x or subtract x from both sides, you get what? 2x minus 4 greater than 0, right? Then add 4 to both sides, you get 2x greater than 4 or x greater than 2. Do you agree with that? I think that's, you tell me if that's right. All right.
Yeah.
Well, what's the probability of x greater than 2? Without doing it, just tell me. Take this f of x, right? And I mean, don't mess with y. Take this f of x and integrate it from 2 to infinity, right? I'm not going to do that one, but does everybody see that? It's meant to be very clear and obvious if you can take the statement of the problem and turn it into a mathematical statement. Okay. Is there another part? I think that's it. By the way, please do these problems before Friday. Now, the next stuff I want to talk about, now we're going to get into expected value of x, the mean squared value of x, the squared value of x, and any other form of, these are real, this is actually very important. It's used all the time. I use this in radar. I mean, this type of, these theorems and what I'm about to show you become very, very important in a lot of the stuff you're going to encounter later in the curriculum. You haven't taken communications yet, have you? Mm-hmm. All right, well, you're probably going to have Dr. Tugnate, and a lot of communication work is the probability that something is going to occur, especially errors. The probability of an error, and he'll probably get into that in terms of the digital transmission. I don't think they'll do it that long. All right, just to review. I'm going to look at this section. Now, you're going to see this on Friday. I can be clear. You're going to see this on Friday, this type of questions related to this. Anytime you talk about the expected value or mean value, there's a lot of ways to show it. Most of the time, they have X bar, a bar over the top. They also, in your calculators, will use the symbol U. Don't ask me why, they just do. And it's been done since I've been in school. And they also show this as the E, meaning expected value of X. Correct? So in terms of the probability density function, it will be an integral from minus infinity to infinity of this operator X times f of X, and I'll make it a small x, sorry. X times f of X dx. That's it by definition. Now that is if it's a continuous value. Y'all follow me? If it's a discrete value, then if you have discrete, like if you talk about, the number of heads when you throw a coin up 4 times. So you can have no heads, 1 head, 2 heads, 3 heads, 4 heads. Follow me? Each of those has a probability of occurring, if you, assuming the event is tossing a coin 4 times. That would be discrete. And in a discrete case, then there would be a summation here. And it would be the summation of, and I'll call it x of I, where I goes from, and this is really going to be from 1 to n. Now, when you have that, the first value might be 0. Do you follow me? The first value when I is 1 may be -1. You don't care about that. What you care about is this form. That represents the very first value when I is 1. Then it would be the actual density function. This would be, you could call it the probability of x equal xi, and you would sum them up, and that would be the mean value. Follow me, class? Now that's for the Bernoulli trial thing, for instance. I'm not going to go there right now, but everybody get the idea. It can be either continuous or discrete. I'm going to do continuous on the quiz. There. You wanted to know what you had to know. Now you know. Next, agreed with this? The next thing we're going to talk about is, in general, the form is anytime we have this capital E, it's an expectation operator, and any function in here, if you have g of x, the expected value of g of x is simply the integration of g of x weighted by the probability density function of x dx. That's all it is. The first one, the mean value, is very important for x, and there are 2 other values that become very, very important. The next value, after the mean of x, and this is called the mean squared value. Now, it's the expected value of, and I want you to see this, it's mean squared value of x squared, of x squared. Follow me? Now the function g of x is x squared. This is often symbolized, and you've got to be careful looking, as x squared with a bar over it. So anytime you see a bar over anything, it means the average value of that anything, any function. And that, as you might expect, is the integral from minus infinity to infinity of x squared times f of x dx. That's it. Can you all follow me? Now, and by the way, this is going to be, they'll call it the mean squared value. Then there's going to be the variance. And the symbol he uses is VAR, variance of x. But really what this is the expected value of the quantity x minus x bar squared. Now I'm going to show you something about this. this is important, you pay attention here. Remember, this value of x bar is a constant. We don't know what it is, it's a constant. With me on that, class? I don't know what it is, but anytime you have a density function, and this assumes there's a known density function in order to get these things. If we don't know that, we can't get any of this. So you can break this up into the expected value of, this is important, of x squared, just complete the square here, x squared, and then they have minus 2x x bar, and then plus x bar squared. I'm going to get out of the way, just see what I've done there. I've taken and completed the square operator. Everybody with me on that? Okay, you take a look at that. Now, anytime you have expected value of A plus B plus C or anything like that, you can break it out as expected value of A plus expected value of B plus the expected value of C. Follow me on this? A linear, these are all linear operators here. So I can say that this, in fact, is the expected value of x squared minus 2 times the expected value of x times x bar, and then plus just x bar squared. Because the expected value of a constant, without ever saying it, the expected value of 2 is 2. It's a constant. Do you follow me? There's nothing tricky. Here's the one you got to be careful of. Now, x bar is a constant. I want to make sure I get your attention on this one. You agree with this, class? If x bar here is a constant, see it right there, I can pull that in front of the expectation operator. And that means this is minus 2 x bar times the expected value of x. What is the expected value of x? X bar, it's the mean value. Can you all see that? So this means this part is just going to be it's going to be x bar squared. Can you follow me on that part? Now you can probably see where I'm going. Take a moment. Can you read my writing? Okay.
Yeah, I was writing it. Can you expand it again? I was writing it down.
Yeah, here's what happened right here. When I had the expected value, I had the expected value of 2, this is right here, 2x x bar. That x bar is a constant, right? That's the same thing as 2x bar times the expected value of x. The expected value of x is x bar. It's the average value. So it's really going to be, all this is going to be expected value of x squared. And I'm going to do this. I'll put it the way it's symbolized in the book. They'll take x squared and put a little bar over it. Minus 2x bar plus x bar squared. So this means it's just, this whole thing boils down to x squared bar minus x bar squared is equal to, and the variance symbol is sigma squared. This is the variance.
Yeah, that was getting really weird in the book. I'm like, it's hard to differentiate. Is it x squared bar or the square of x bar? I was like, what is
My eyes are
happening?
getting worse and worse the older I get. Anytime you have a bar, look what's under the bar. All right, so under the bar, and this one's a square. It's taking the average value of the squared operator. And here you have the bar is over x, so it's the average value of x, but you're squaring whatever that average value is. Now this is a real important thing. You need to know this for Friday. And I hope I'm clear on that one. So now, the best way to see this is applied. Honestly, I could talk myself a little in the face, and I don't prefer to do that. So, what is it? Do you have, here, I want to do problem 2-4.1, and here, let me if you don't mind reading it. Trying to do these kind of fast and get to the points. I don't want to go too fast, but I got 15 minutes and it's perfect. I'm on schedule for once. I'll tell you, there's some stuff coming up, and in terms of abstract thought, things you really, you don't have like a physical analogy for are coming up. And this requires, you gotta be focused, because some of this stuff, I hate to say it, but it kind of drives you nuts if you're not careful. All right. Okay, 2.3, 2-3.2, I gotta remember what that was. Hold on for 1 second. I gotta erase this. I'm gonna apply it to this problem, but I've gotta get, in order for me to do 2-4.1, I need to get the probability density function from a section, problems in section 2-2. How many tried this problem? I think I put it up there, right? All right, if you haven't, please be attentive here. So this is problem 2-4.1. Now, I'm going to give you the density function from the earlier problem, so you don't have to go back and take a look and calculate. The one they use is f of x is equal to, you tell me if this is right, e to the minus x minus 1, and it's really for, or times u of x minus 1. So it's basically for x greater than 1. He doesn't,
Where's that?
2-4.1 goes back to 2-3.3, I think that goes back to 2-2.3 or something like that. It keeps going back. And it needs the density function from a cumulative distribution function. Did you look at those problems? I think he did. I think this is a density function for him. All right, so what does he ask first of all? 4.1. Be careful.
For the random variable, find the mean value of x.
All right, now, this is the density function, right? The smart move when you're taking a look at a weird density function or something you can't see real quick is to sketch it. This is f of x equal to e to the minus x minus 1 u of x minus 1. And it looks like this. At 1, the value is, if you take a look at that, that is going to be 1. It's e to the 0. And then it just monotonically decreases. Can you all see this, class? Now, if that's the density function, you want the mean value of x, I'm going to tell you a trick. We're going to work it out brute force, but I'm going to tell you a trick. You see how this is a Gaussian from here off, up? If this was centered at 0, anytime you have a function, and I'll just say this, the expected value of x, well, I take it back. I'm going to do this. It's going to confuse you. I'll just do it this way. Whenever I look at this, I want the expected value of x, right? Go right to the formula. You know, technically, it would be the integral from minus infinity to infinity, right? But you'll notice this one starts at 1. So we don't start at minus infinity. We start at 1 to infinity. So then I'm going to go ahead and integrate from 1 to infinity of this, or I got to take x times that, which is e to the minus x minus 1 dx. Everybody follow me, right? Can you see it back? I'm always worried about my handwriting. Can you see it?
Yeah.
Okay. How many have their calculators here? You could, I think you can plug that right in and you should be able to get it. But I'm going to just simplify it a little more. So this is really equal to, and I'll go the integral from 1 to infinity. And here I can take out the e to the, or I've got x, e to the minus x. This is an integration by parts, dx. And then I break out e to the 1 here. Here's what I did. I simply broke up that exponential. Instead of e to the minus x minus 1, it becomes e to the minus x plus e to the, or times e to the 1, and I pull out e to the 1 here. Follow me? Are you with me on this, class? Now you can do this with UDV, right? That kind of integration, back in the past, I think there's professors that, people, I don't know if Reese did this, never have calculators in this class, and they had to do the integration by parts, which I think is a little overkill. But if you wanted to do it by parts, if you have x e to the minus x dx from 1 to infinity, you let u be x and du be dx, and then you would have dv equals e to the minus x dx, and v is equal to minus e to the minus x. Do y'all remember doing these things back in the day? All right, probably don't like to do them. I don't like to do them when you have to do them like 2 or 3 times to get the final answer, but this is integration by parts. If you want to do it that way, then you're going to have, this is uv here, minus integral of v du from 1 infinity, 1 to infinity, and it's actually going to be minus and what's that going to be? And the whole thing's times e to 1. So, I'm running out of room for patience too, so this is going to be, flip that, I got e to the 1 times 1 e to the minus 1. And for this one, I got plus e to the minus 1. And what is that going to be? That's 2. All right, so I got 2 for the average value. Anybody else? Did you do it in your calculators, anybody? Did you track your calculator? No. It'll be 2. And I'll tell you one other thing, that anytime you want if you have an exponential, if you have a density function, f of x equal e to the minus x for x greater than equal to 0, and you want the expected value of x, what he'll do is actually have this. If we have, I'm not even going to, there's these tricky formulas, but if I put them up here, the formulas for this, and I know the expected value of something where expected value of a density function that's just e to the minus ax dx. You follow me on this? The expected value is going to end up being simply 1 over that coefficient. It's usually e to the minus ax. It'll be 1 over a. For this one, it would be 1 over 1, because the coefficient, if you just had the expected value of, I don't mean to go off on a tangent, but if you had f of x equal to e to the minus x u of x, and you wanted the expected value of x here, let me do it this way. Ax, and this is going to be times a, has to be times a. This expected value of this will be equal to 1 over a. I guarantee it. You can go ahead and prove this is a mathematical proof. It'll be 1 over a. In our case, if we took the expected value, if we shifted the 0 point to this point, the expected value of this density function, that's 0, not 1, is going to be 1. but it's skewed by 1, so the expected value would be 2, and that's what we got. I promise you, there's some tricks you'll see as you're doing these things, but your calculator, did your calculator do it?
No, it gave me an error. So I needed to get like another package or something.
Well, I'm sorry, but I know the calculators do these things, because I've taught this class since 2022, and I know they do that. Anyway, I wanted to go through that one. What else did they ask in that problem? I'm sorry.
The mean square value of x.
Let's see that. Does it ask all 3 things?
Yeah, it does. It's on the screen.
All right. So now he's asking for this. This is integration by parts twice. This is the reason I would recommend you use your calculators. So now what he's saying is that density function that I had before, he wanted, try this out. If you have a calculator, try it out. He wants the expected value for that. That's strictly the integral from, in this case, 1 to infinity of x squared, follow me? Whatever this function is, that's what you put there, and then times f of x, which is going to be e to the minus x minus 1 dx. Now there's tricks to this. I do not like doing integration by parts twice. That's what you need to do with this. That's the reason I'm saying get your calculators out and you can learn how to use it. You can do it that way. You can do integration by parts twice. I'll tell you how you break it down. You probably could do it a couple ways. You could say, for this one, if you let u equal to x minus 1, then du is equal to dx. So this integration would be equal to the integral, and therefore x would be equal to u plus 1. You would have u plus 1, and it would be squared, times e to the minus u and du. And then, so if x was 1, u would go from 0 to infinity. I'm going to do this one time, but you all follow me? This is a simple substitution to make the integral easier. It's the only point of this. Well, when you square that out, now what you're really getting is an integral of u squared e to the minus u du, and we'll go from 0 to infinity. Then you're going to have plus, if you look at this, it's going to be 2 times u right here, because you're going to get that twice, plus 2 times the integral of u times e to the minus u du from 0 to infinity. And finally, you're going to get plus the integral of e to the minus u du from 0 to infinity. Are you with me? All right. This one right here is going to be 1. So it's going to be plus 2, plus the integral of e to the minus u du from 0 to infinity is 1. You all with me on this, class? And this one is something you got to do by parts twice. And that's going to be 2, I believe. Does anybody have a calculator that can do that one? Do me a favor. Use your calculators, make sure you can do this. All right? I put the solution for this one up. That's correct. All right. But the integrations at this point can be irritating. So your calculators are godsends. I'm not trying to give you difficult integrations, but just be aware that those exponentials always end up with integration by parts, and they tend to irritate me. I don't have time for that one, but I want to just do one last point. I think you get the idea that if we had the mean squared value that we calculated there, I think the answer is 5. Can anybody verify that? the solutions. I should flip them over, but I think it's 5 for the mean squared value. All right, if it is 5, which it is, now I gotta ask you this, what's the variance? So the mean squared value is 5, the mean value is 2. Hold on for 1 second. This is one point I wanna make sure I make. I think today it's not gonna rain. I think. So when I talk about sigma squared, which is the variance, all right, I mean, we've got the mean squared value, we want the expected value of x minus x bar squared. And that, I just put up there, is equal to what? X squared bar minus x bar squared. You don't have to do it if you did the earlier ones. And there's tricks to this too that I'll show you on Friday. With me, class? All right, what's this gonna be? Well, we figured out this is 5, right? Or at least we tried to figure it out. It is. Minus, and this was,
2.
be careful, 2 squared, right? That's where you make mistakes. So it's 2 squared. That's 5 minus 4 is 1, right? And here's something I have to tell you. The variance is really how much, whatever the function is you're looking at, how much the statistics vary from the mean value. And that's why for professors, when they look at the average value of the class, it may be 70, it may be 80. That's not the real thing they look at. They look at the variance. Because if you get a big variance, then the square root of that standard deviation. So a lot of times they'll look at the standard deviation. And if the standard deviation is more than about 1/6 of the mean value, you know you got a lot of people who don't know what they're doing. I mean, it's skewed all over the place. And that's the scary part for professors if they're trying to teach people effectively. If it's a weed class, it's different. I mean, if you're down, physics 1 and 2 and calculus, you're gonna get huge spreads because you got kids that can and can't do math, and they're gonna, the ones that can't, flunk. But you're here and you're juniors, you went through all that stuff. So when a professor sees a huge variance, it means either one or two things. Either it's football season, we're doing well, so nobody's studying, or it means the guy's not effectively teaching the girl, and he has to do something else. That's the truth. It's just the way it is. All of you by now know that you're capable, but whether it's on me or you,